Yeah, I mean, there's an hour in between anyways, because they're 3-hour blocks and I'm only doing 2-hour tests. So, and you'd probably finish a little early. I try not to make them like race against the clock kind of tests. So, you'd probably get a good little break anyways.
Maybe get something to eat, so you don't fall asleep in the second one.
Yeah. Okay, so number 3 from the homework. Okay, so the disk is rotating around that pin where the coordinate system is shown. And then the arm is rotating, I guess it's oscillating up and down according to that. All right, so which one of these motions affects the axis of rotation of the other one? No matter what the position the arm is in, the axis of rotation of the disk is the y-axis, right? You with me? The Smoot-Hawley tariff bill, did it raise or lower? Raise or lower? That's from Ferris Bueller. Okay, so the horse has to be this. If you change the orientation of the disc, it changes the axis of rotation of that arm, okay? You have to see that in order to think about this right. You with me? And so this is the cowboy or cow person.
Always mean that the arm is along the x-axis, by facing the orientation.
Yeah, that's right. Okay, and now we're trying to calculate the acceleration of the end of the arm. So we're trying to calculate the acceleration of this point here. Well, I'll call it P. Okay, so we know we're going to use a rotating coordinate system. This one, it tells us where to put the coordinate system. We want to put it right on that axis of rotation of the disk. But if it doesn't tell you where to put the origin, there is something that you want to do. And I'll show you what would happen if you didn't make this choice too, and after I'm done with this. But there's 2 ways that coordinate systems can screw you over when you try to go to Newton's laws. Okay? One is rotating, and sorry, this is rotating. We can't do anything about that. The other one is that the origin is accelerating. And so we would prefer to always put the origin at a place that is not accelerating. Okay? So even though this coordinate system is spinning around with the disk, as this problem goes, we want to keep the origin fixed at this location where it's not moving. Okay? So there's infinitely many places on the horse where you could put the origin of your coordinate system. But notice this is the only one that has 0 acceleration of the origin. Okay? Like if I put it here at the hinge, that's in circular motion. So we know that that's accelerating. Okay? So anyways, you want the coordinate system fixed to the horse, and you also want the origin at a place that's not moving. All right, and we're trying to calculate the acceleration of P. So we know we're going to use one of these 2 formulas. So the acceleration of P is equal to the position components double dot plus the angular acceleration of the coordinate system crossed with the position vector plus 2 times the angular velocity of the coordinate system crossed with the position component single dot plus omega cross quantity omega cross p. Okay. We could write this a different way too, and you always have to think about which one is useful. So the acceleration of that point P can also be thought of as the acceleration of that point P that's observed in the rotating coordinate system, observed by the rotating coordinate system, plus omega dot cross P plus 2 omega crossed with the velocity of P that's observed in the coordinate system, plus omega cross quantity omega cross P. Okay, so which one of these two is useful to us in this problem? In most of these kinds of problems, the one that's useful is the second one, because taking the time derivatives isn't usually possible in these cases where we have multiple circular motions going on. But for this one, it actually, it's the top one that we want. And the reason is that we can come up with an expression for the position of that point P as a function of time. Do you see that? Do you see how we're going to do that? I mean, that's just going to be the length of this thing times cosine and sine of theta. And theta is going up and down. Okay, so if we're using this red one now, we can start organizing our information. So we know that theta dot, not theta dot, theta of t is equal to sine of t. And so the position vector, okay, so now here we have to use the definition of the position vector. So if the origin was at that hinge, this would be 0.3 times cosine of theta, 0.3 times sine of theta. But then we also have an additional 0.5 to get from the real origin to that hinge. So the position vector as a function of time is equal to, in the x direction, 0.5 plus 0.3 times the cosine of theta. And theta is equal to sine of t, so this is the cosine of sine of t. And then for y, the height is just going to be 0.3 times the sine of theta. So 0.3 times sine of sine t. And then this isn't moving in the z direction. So this is just equal to 0. You with me on that? Now the other stuff we need, I guess I'll do the derivative stuff first. So the components dotted are, we have 0.3, this is going to be negative 0.3 times the cosine of t, I'm trying to do the chain rule stuff in my head here, times the sine of sine of t. And then the second one is going to be positive 0.3 times, and we have the cosine of t times the sine of t times the cosine of sine of t, and then 0. Are you with me on that? And then the second derivatives of the components, so px double dot, py double dot, pz double dot. I don't mean the acceleration. I mean, so remember that this is a rotating coordinate system. And so taking derivatives, time derivatives are weird in rotating coordinate systems. So what we're calculating is what the coordinate system thinks is the time derivative of this vector. Okay, so what we're calculating is the observed velocity and the observed acceleration, but that's not the same thing as the true velocity and the true acceleration.
When you say observed, you mean observed from like the origin that we've set up?
So imagine that coordinate system being a camera that's rotating with the coordinate system. And that camera is watching that point at the end of the beam go up and down. And that is the observed motion that that camera sees. If the camera doesn't have any way to know that the disk is rotating, the camera only sees that point moving up and down.
When we first discussed the accelerations of velocity, was very kind of viewed from like an outside perspective, but this observed velocity and acceleration is within the coordinate.
Well, really, like we've always thought of velocity and acceleration as observed. Mm-hmm. It's just that in the past, our coordinate system was not rotating. And so the true velocity and true acceleration were what the coordinate system observed. Now, in a rotating coordinate system, there's a mismatch between those. And the mismatch is all of these later three terms in this expression for acceleration.
So the camera is always going to be on the origin?
Well, I'll do one today where we move it away to make it a little harder, but it'll help your sort of understanding. But yeah, if you get to choose where the coordinate system origin is, always put it somewhere where the origin isn't moving. Okay. Otherwise, you have to use relative motion.
But here the origin is moving.
No, the origin is staying at the same spot. The origin is just a point, and it's staying at the same spot. It's only the axes that are changing orientation. Okay? So those are two different things. So try to separate those in your mind. It's hard. I mean, so I'm saying this with emphasis, so everybody is making this mental note. But the origin can go places, and totally independently of that, the axes can change orientation in time. And those are two separate problems that you have to deal with, potentially. If you put the origin at somewhere where it's not moving, then one of your problems is gone, and you can just worry about the rotating coordinate system.
But in this case, you put the camera at the origin.
That's right. And so all the camera's doing is just turning around, looking at different angles the whole time. Okay, so now we got to take the second time derivative of this. So let's see, we got 0.3 sine t times sine of sine t. And then we have to use the product rule. So this is minus 0.3 cosine t times cosine t again times cosine of sine of t. So horrible. And then the second one says So we have negative 0.3 sine t times cosine of sine of t. And then minus 0.3 cosine of t, and then cosine of t sine of t, and then 0 for z. So if the coordinate system didn't know it was rotating, this is what it would think was the velocity and acceleration. It turns out it's not, though, because the coordinate system is rotating. Okay, now we can simplify this a little for our calculations because we're told that we want this at time equals 5 seconds. So, okay, I have to plug 0.5 radians in for all this. How do you know, by the way, that this is in radians and not degrees?
Just a natural assumption that we do.
It has to be a natural assumption anytime you're taking derivatives or doing integrals of trig functions, because otherwise the chain rule doesn't work. Okay, so anytime you take derivatives or integrals of trig functions, you need to be in radians. Okay, so let's calculate these. I'll turn. Okay, so there are my, that's my position vector and my components dot and my components double dot. And the only remaining thing that we need is omega and omega dot. So the disk rotates with an angular velocity of 0.1 t. That is in the y direction. It says that the angular velocity omega of the body is 0.1 t. But notice, so always be clear, are you dealing with a lowercase omega, an angular velocity of the body, or an uppercase omega, the angular velocity of the coordinate system? Well, in this case, there is a body with an angular velocity of this. It is a lowercase omega if you're working with that body. But what we really care about here is the coordinate system is doing this with the body. So our capital omega as a function of time, and let me get this out of here. I'll just substitute in. So this is 0, 0.1 t, 0. And so if you plug in 0.5, you get 0.050 at the instant we care about. And now we need our omega dot. And we have omega as a function of time. So this is just going to be 0, 0.10. And now finally, we can just plug all this stuff in. So the acceleration of p is equal to negative 0.139, negative 0.2340, plus omega dot times the position vector, so 0, 0.10, crossed with the position vector, 0.766.138. Plus 2 times omega, which is 0.050, crossed with the single dot of the position components. This one's negative. I think that's right. And then plus capital omega crossed with capital Omega cross position vector, and the position vector was 0.766, 0.138. All right, so we'll get here is that the acceleration of that point P at this instant is negative 0.11409, negative 0.234, negative 0.0645. Any questions about that?
We would do a relative thing from here if it was not set on the origin.
Yeah, let's not do that for this one because this problem already is so has so many sort of confounding calculations and stuff. So let's do that with a more kind of basic problem, but I'll show you how that works. Any other questions on this one? All right. Well, now that you have that acceleration, like what's the point? If there was one point to doing this, there basically is. What's the point of doing this calculation? The point of doing all this is that this now is an acceleration that we can use in Newton's second law.
So like how much of a force the end of the rod would apply?
Yes. So exactly. So if there was some kind of payload sitting here where this P is, and you knew the mass of it, and you knew that this acceleration was going to happen, that this motion was going to happen, this would let you calculate the force that you would have to apply to that small object.
So this acceleration is with respect to the origin.
Well, okay, so acceleration, it is in that coordinate system. We did this at a single instant, right? And so at the next instant, that coordinate system is going to be in a different orientation because it's rotating. But this calculation gave us the acceleration vector in exactly the orientation of that coordinate system at this instant.
Wait, can you repeat that?
Yeah. So, I mean, this stuff gets confusing because, like, what does that coordinate system even mean? Like, in the next second, that coordinate system will be something else, But the vector that we got is the acceleration vector exactly expressed in that coordinate system at that instant. So a positive x component means straight to the right. A positive y component means straight up, and a positive z means out towards us.
Could we take a magnitude and just the acceleration as a way to express it in all instances?
Well, we didn't do this in all instances anyways. Really, this calculation, there's never a reason that the magnitude would help you. Like, if you had a way to do this as a function of time, you would just keep it in vector form. Which I guess we could have done. It just would have gotten horrendous, That's why I gave the 0.5 here, the 0.5 seconds. We could have carried all this through. You would have just been doing cross products with these crazy functions of t, But what we would have gotten was an acceleration as a function of time. And at each instant, it would have been referencing the coordinate system at that instant, which is a little confusing.
If you were to take the magnitude from several instances, would they all be the same since there's no change in the rotation of it?
It is changing. It has a constant angular acceleration. Yeah. And then that arm is moving up and down, so it would change. Yeah.
So for these type of problems, we're not going to use the watermelon version.
In this case, we didn't have to, and the reason is, so that's kind of the key thing you have to notice to determine which form of this acceleration you use. If instead of giving you this as a function of time, I said that this was just moving in circular motion and said at this instant it's in this position and it has this angular velocity and this angular acceleration, then you would have used this form and used the watermelon equation. But basically, anytime you're given something as a function of time, that should just trigger you to think, I'm probably using this form if it's a rotating coordinate system thing. The only reason really that I would ever give you a function of time is so you can take the derivative. Okay. Any other questions on that one? That's a hard one. I mean, really, it's not conceptually that hard, but the combination of the conceptual that's new with sort of painful calculus makes it feel bigger maybe than it is, Okay, let's do an example. Go back to something a little simpler. So let's say that we have a hinge attached to the ceiling. And a bar like that attached to the hinge, and then a second bar attached like this to a pin coming out of the first bar. And the length here is 1 meter. And the length here is 0.8 meters. And we'll say that this one has the vertical member has an angular velocity counterclockwise of 5 radians per second and an angular acceleration clockwise of 40 radians per second squared. And then the second one is rotating in a circle that goes into the board, out of the board, into the board, out of the board. So we'll think of that as going this way. And that's 20 radians per second. And this is our point P, and we want to calculate the acceleration of that point P. And after we do this, so for this one, we can use any coordinate system we want. After we're done with it, I'm going to put the coordinate system in, I'm going to purposely choose a kind of trickier location for the coordinate system and show how it all kind of fits together and that we get the same answer if you do it right. But anytime you get to choose, you want to put your coordinate system at a point with no acceleration that's not moving at a fixed point. Okay, so which one of these is the horse? The vertical or the horizontal? The vertical is the horse. Does everyone see that? Okay, yeah. Well, so think of the axes of rotation of both of these things. And then think, does the motion of the other one change the axis of rotation? Okay, so first think of the axis of rotation of the horizontal member. Okay, Right now it's vertical up or down. What if this moved a little bit? What if it moved 45 degrees this way? The vertical one moved 45 degrees this way. Now the axis of rotation of this would be at a 45-degree angle. Okay? So the axis of rotation of this horizontal body depends on the orientation of this. So that makes this the horse. But then you could check the other way to make sure, you know, Sam, do you check it? Does it work the other way? Well, right now, the axis of rotation of the vertical member is into or out of the page. Okay. Well, what if you move this to a different spot? Now you move this so it's facing out of the board. Does that change the direction of the axis of rotation here? No, it's still out or into the board. And so both of these tell the same story. This is the horse, and this is the cowboy because it's riding the horse. Okay. That cowboy and horse thing is trademarked by me. That's how I get most of my passive income. And the watermelon equation. Okay, so where do we want to put the coordinate system? We want to put it on the horse, but of course there's infinitely many places on the horse that you can put the origin. Okay, so of all those infinitely many places, where do we want to put it?
Pin joint?
At the pin joint, exactly. There's one place on that body that's a fixed point, and that's where we want to put it. So, so my coordinate system is going to be, I'll go X this way, Y this way, and then Z would be coming out towards us. There's nothing given as a function of time, and it's really just about as simple as that. I think it might always be as simple as that, but at least most of the time it is. We're going to use the form that says the acceleration of P is equal to the observed acceleration of P. You know, rather than the second time derivatives of the components, we're going to use this form because we don't have anything as a function of time. Plus omega dot cross position vector plus 2 times omega crossed with the observed velocity vector of P plus omega cross quantity omega cross P. And all we need to do now is collect each one of those individual vectors and then do all the calculations. So in this 4-term expression, which one of those 4 terms is called the Coriolis acceleration?
And that's 2 times.
Yeah, the one with the 2, that's, yeah, is the Coriolis. Pretend Coriolis is a different language for 2. And then what's the major significance of the meaning of the Coriolis acceleration? There is none. It's a stupid thing to have named. But if you use that word to your professor at the U or wherever, they'll think you're smart, you know. If you say enough smart things, your professor will give you an A. Okay, so let's collect these things. So the first, so let's get capital omega first. So that coordinate system is rotating. The angular velocity is 5 in the positive z direction, because if you rotate your hands like that, your thumb is in the positive z direction. And so omega is 0, 0, positive 5.
So the vertical member is rotating like to this guy?
Yeah, it's in a circle. So like if you track the motion of, so forget about this one for a second. And if you track the motion of this point, it would be like moving in a big semicircle like this.
Okay.
And then this one would be moving in a big circle like this if you stop the motion of this one. Okay, so we have omega, and then omega dot. So this is the angular acceleration of the coordinate system. And that one is, use the right-hand rule. That's my left hand. Don't do that. So that is this way. So it's in the negative z direction.
And it's just, you said, capital omega because it's just like
Because the capital omega says that that's a rotation of a coordinate system, not a rotation of a body. Okay, I mean, this also is the rotation of a body, but the key thing is what we care about here is the rotation of the coordinate system.
So capital omega is always gonna be like the alpha.
It's capital omega dot is the alpha of the coordinate system, is the angular acceleration of the coordinate system. And capital omega without the dot is the angular velocity of the coordinate system. So this is 0, 0, negative 40. And now we have to collect the position and the velocity and the acceleration that are observed in this coordinate system. Okay, let's do position first. That's a good warm-up. So what's the definition of the position vector? From what to what? That's right, from the origin to the point of interest. So that goes all the way from up here is the origin down to P. So that's going to be 1 in the negative y direction, and then 0.8 in the negative x direction. Okay? Yeah, in the negative. So, yeah. So negative 0.8, negative 1, 0. Okay? Those two distances are just different. Yeah. And now we have to figure out the velocity vector. So how are we going to come up with, so now we're looking for the observed velocity vector. The velocity that's observed by this coordinate system as this thing moves. My shirt needs another button on the bottom. It's like a midriff.
So this is like it's like respect to ground.
Well, not really, no. This is, so remember that this coordinate system is a camera that's rotating, okay? And so as it rotates, this, as this whole contraption goes, it's a really complicated motion. But to this camera, it's actually a very simple motion, because since the camera is rotating with the horse, all that camera sees as this whole thing moves around is this P just going around in a circle. It's just a simple circular motion, okay? Because like, imagine the camera looking this way. Right now, it just sees P as like straight up in front, in front of it and up a little bit, okay? And then once it moves over here, it would still see it there, yeah. That camera doesn't see anything about the motion of this. It only sees the motion of this in its reference frame. And so all it sees, and you can think of it as just forget about the motion of the horse, just pretend it's not there and just visualize what the other thing is doing. This is just in a circular motion going around the y-axis. Okay. So yeah, think of, so when you're trying to think of these velocity and accelerations observed in the coordinate system, I think the easiest way to do it is just imagine stopping the motion of the horse and just think about the motion of the cowboy. Okay, so this is going to be a circular motion. And so the expression is omega cross r. This is little omega, because the omega we want here is the omega of this horizontal body. So now let's put these two in. So little omega is going to be, come on. So that is going to be about the, y-axis, but in the negative direction because the right-hand rule, 20. So 0, negative 20, 0. 0, negative 20, 0. And then someone tell me the definition of the r vector.
The
Center of the circular motion to the point of interest. So it's different than the p vector. So you got to be careful. In this problem, sometimes they're the same, but in this problem, they're different. So the center of the circular motion is just this pin here. And we're doing the vector 2p. So that's just going to be 0.8 in the negative x direction. So r is just going to be negative 0.8, 0, 0. And so V observed is 0, negative 20, 0, crossed with negative 0.8, 0, 0. And that is 0, 0, negative 16. Yeah.
Shouldn't we use relative motion? Because the velocity observed is not about like from the origin.
Nope, you don't have to do that. So that really is the difference between what R is and what P is. So if you're, don't draw this, and I'm going to erase this, but like if your coordinate system is over here and you're calculating a circular motion of this, let's say you want to calculate the velocity of that point in that circle, your R vector is just this. Okay. It doesn't matter where the center of the circular motion is, all that matters, like vectors don't care about locations. They only care about magnitudes and directions. And so the velocity of this point is in this direction, no matter where the origin is. Okay. And so there's only one left, but it's the most involved one, but we're going to use the watermelon equation to calculate the observed acceleration. So this says alpha cross r plus omega cross quantity omega cross r. Yeah, so remember that these are, for this observed stuff, we're pretending that the horse isn't moving. So these only represent the motion of the cowboy, the second body. And that's always how it's going to work. And the cowboy doesn't have any angular acceleration in that coordinate system. So this is going to be 0. And so, well, we already have omega and r. Omega is 0, negative 20, 0. R is negative 0.8, 0, 0. So the acceleration is 0 plus 0, negative 20, 0, crossed with the quantity 0, negative 20, 0, crossed with negative 0.8, 0, 0. Okay, and we already calculated this. These two together give us 0, 0, negative 16. And so then cross these two together and you get 320, 0, 0.
So for, B observed and A observed, they're always gonna have the same rate, the same vector.
Yep, that's right. So this observed acceleration is 320, 0, 0. And now finally we can put all this stuff together. So our acceleration of P is the observed acceleration plus our omega dot is 0, 0, negative 40. Crossed with the position vector, negative 0.8, negative 1, 0, plus 2 times omega, big omega, so that's 0, 0, 5, crossed with the observed velocity of P, which is 0, 0, negative 16. Since those two vectors that we're crossing are parallel to each other, this one is going to be 0. And then 0, 0, 5, capital omega, crossed with the quantity capital omega cross P. And then we just have to put this all together. All together, we have that the acceleration of P is 300, 57, and 0 for Z. So, you look at this and I mean, it's just absolute chaos what's going on. I mean, trying to imagine what's happening with accelerations there. There's no way to do it without this approach. But if you separate it into the two separate motions, the motion of the horse and the motion of the cowboy, you can define all of these variables, write out the equation, and it's just a nice systematic thing that I know is hard at first, but after you do a bunch of these, it'll start to feel sort of repetitive, which is what you want, Any questions about that one? Okay. So what would be different here if we didn't put our coordinate system here, So we know our coordinate system has to be fixed to the horse. Okay, we don't have any choice about that in order to solve this problem. But what if instead of putting it here, we put it here, say? Okay, how would that change things? Well, then the origin of our coordinate system is accelerating. So we have to deal with that. And so we have to use relative motion. And so we're definitely not going to get through this problem, but I can at least sort of set it up. So now, what if the coordinate system was fixed to the horse? at the bottom. Well, now that's not a fixed point. So the origin is not fixed. And so now we have to use the acceleration of, so the acceleration of P relative to the ground, which is what we want, is the acceleration of P relative to, let me label these. So this is the ground. Let's call this one the point B. So the acceleration of P relative to the ground is the acceleration of P relative to B plus the acceleration of B relative to the ground. And this, we're going to use the rotating coordinate system approach. This, we're just going to use circular motion. So this is going to be the watermelon equation. And when we add those two up, we'll get a total expression for, so we'll get something that looks different coming out of the rotating coordinate system equation. But when we add it to the watermelon equation, we'll get the same thing. Okay. What?
Was B? Was from
B is the hinge there. That's not a very good color to use, but that's where our coordinate system is now. So what if the coordinate system was fixed to the horse at that point B?
In which case your P vector would be different, right? It would just be -0.8.
Yes, that's right. So now our P vector is the same as our R vector.
Yep.
And yep. Okay, so the circular motion, this is the acceleration of B relative to the ground. So that is just the problem of this circular motion that B is following this way.
So would that still like work?
That's fine. All you need is an infinitesimal part of the circle. Yep, it doesn't have to be able to go through the full range of motion. Because remember that all of these calculations are instantaneous. Let's stop there. We'll get into this next time. So okay, I'll give you a couple more problems to work on. Because I know you kids love problems.
We got another week.
Kids today and your problems. Yes, we have one more week of this class. So this is the last topic we're going to do in this class.
What about the mechanical?
Yeah, we just didn't get to it this semester. So.